Hi everyone, my name is Reagan and today I'm going to show you how the simple vibration of a guitar string can help us understand what light truly is. Even though light and sound seem totally different, one you could see, one you could hear, both are governed by the same physics of waves. To show that connection, I'll walk you through two key ideas. The first one, how the wave equation comes from the tension and motion of a guitar string, and the second, how light waves change when they move between materials, as shown when you change the length when you fret a guitar. Now let me share my screen really quick. Perfect. Here's our guitar string when we pluck it. As you can see, a small segment, all segments of it will be pulled upward, but by a different amount. So we'll say our X, the small segment of the string is delta X, pulled up by delta Y. And we have tension being pulled on both sides. Now, because that tension is slightly curved, because the string is slightly curved, the tension on both sides do not cancel out perfectly, and that creates a net upward force. From Newton's second law, we can say that force equals mass times acceleration. And the vertical force of this tension can be written as tension times acceleration in its derivative form, dx. And we'll just show acceleration being here on the string diagram. And so the mass of segment, we'll say m equals mu dx, where mu is the mass per unit length. And so now we can rewrite this law as the tension times acceleration dx is equivalent to the mu dx times the second derivative over time. So we can cancel out these dx ones right there, rewrite it, and we will have that wave equation of that acceleration equivalent to 1 over the velocity of the second derivative. And we're saying that velocity is equal to the square root of tension over mu. Perfect. So that is the fundamental law describing wave on a string. Oop. Oh, okay. Let me stop sharing my screen. Perfect. And so if you increase the tension, the wave speed increases. That's why tightening a string makes it pitched higher, the wave travels faster, and so the frequency goes up. So from something as simple as Newton's law and a bit of geometry, we get the universal equation for oscillations, the same mathematics that govern the light traveling through space. So now that we know what a wave is mathematically, now we'll find out what happens when it travels through a new medium, like when light enters glass from air. From that, we can look at how physicists visualize waves in k-space. So let me draw another diagram for you. I will share that screen. Okay, So we have air right here, nice and small. Glass, on the other hand, will be larger. So these circles are representing our medians. The air, and n is the index of refraction. So pure glass. So let's say light comes in from this angle. It's here. We have beta for 1, for k of 1. And for light, k is equal to 2 pi times that index of refraction over lambda 0 naught, which is the wavelength. And so that is going through that first median air. Once it hits the glass, this parallel component is conserved. And so we just go right on up to here, and it'll exit out right there. That'll be K2. Okay. So that means when light enters a denser median from air to glass, its wavelength shortens, so the K vector gets longer. In the K vector diagram, each median is represented by a circle. So the radius of that circle is equal to the magnitude of K and for that median. So when a wave hits an interface, this tangential component, like I was saying earlier, is conserved. It goes just right across. P2. And so that's why we can see that that K vector does get quite longer. And from this geometric rule, we can also get Snell's law, which is that index of refraction for the second material over that index of refraction for the first material is equal to sine theta 1 over sine theta 2. Now theta is just going to be here, theta 1, theta 2. So this visualization shows that the direction of the transmitted wave bends, that's the refraction, because its wave vector magnitude changes while the parallel component stays consistent. Now back to the guitar. When we press down on a fret, the pitch goes way up higher, and that is because we are shortening the length L. So we can write that K as the index of refraction pi over L. That's how we can relate it a bit more. So yeah, both actions alter spatial frequency, and therefore the color or the pitch of the wave is also altered. So to conclude, from one small section of a vibrating wave, we derived the fundamental equation of waves, and that then extended the same logic to light itself, using K vectors to show how waves bend and shift in different media. In both sound and light, it's the same language of tension, wavelength, and frequency. A guitar string and a beam of light may seem very different, but they can actually be used to better understand each other. So thank you. It's been awesome to be able to share this with you. Until next time, I guess.